Yeah. Cool. Thanks. You can start the live stream too. I think it's the right ones. Well, it could be the, if it's the previous one, that's also okay. Did you start it? Okay. Yes. Okay, I think we can get started. Today we're going to talk about memory robustness. It's going to be also quite research oriented, but it's also very fundamental. We're going to talk about issues like bit flips in memory that we started last time to motivate part of memory-centric computing, but we're going to go into more detail. Let's see, it's going to be an intense lecture. There are a lot of works in this area that are quite exciting, I think. And there's more to discover, which is the interesting part. Okay, let's see. Oh. Zoom playing tricks. Oh, this is not connected, I think, or I'm not sure. Oh, okay, maybe because of Zoom. Okay, yeah, I see. Okay, I figured it out. Thanks. Yeah, this is another title for this talk. Okay, so this is the work that started a lot of it, actually. I'm going to talk about this one a lot. This is our ISCA 2014 paper. It was rejected once. That's why it's not a 2013 paper. This could have been published in 2013, and then it got rejected, and then it got published at ISCA 2014. It spurred a lot of work on top of this. But I'm going to give you a story, so I'm not going to talk about that directly. How many people know where this bridge is? Yes.
What does rejected mean in this context?
Oh, rejected. Very good. Yeah, basically, when you do scientific work, you usually try to publish it, and you send it to a conference. And the conference decides whether they want to take the paper or not take the paper based on some review process.
Is it limited time slots?
Not necessarily limited time slots. They may consider this paper not so interesting, for example. Yeah.
Because it wasn't peer reviewed or something.
Yeah, basically you sent it for peer review.
Oh, I see.
And when you send it for peer review, that means you get some reviews, and the reviews may not be positive for publication. Initially, when we submitted the micro in 2013, we got not so positive reviews. I'm happy to share them, but we don't have time. They're in the backup slides. If you're interested in seeing the reviews, they're in the backup slides. But reviewers do not necessarily make the right decision, in my opinion. That's why you got to believe in the work and do it in the right way. And then reviewers made the right decision, in my opinion, for the next conference. And I think they were proven to have made the right decision, in my opinion, because there are many papers that replicated this work many times over, and many papers that built on this work also. That's an example. There are many examples of this. This is one of my personal examples, but other people have a lot of examples also, yeah. So basically take the review process with a grain of salt also, because they don't necessarily do the right thing as well, right? Doing the right thing is very important, but people have not figured out how to do the right thing in general in the world. Okay, anyway, without going into more, let's say, philosophy, do you guys know where this bridge is? Yes?
Washington?
Washington State. Exactly, Tacoma Narrows Bridge, yes. But that's the wrong answer, because this bridge doesn't exist anymore. Basically, this is what happened to this bridge. A bit flip, in my opinion, a reliability problem. That's the right answer, basically, in the sense that it used to be there, Tacoma Narrows Bridge. And I think it's a reliability problem, and you can read a lot about it in bridge building, civil engineering, etc. But basically, this is an infrastructure that is very valuable for humans. Today, we're building the computing infrastructure. If we get bit flips in our computing infrastructure, the consequences will be much worse than this, in my opinion, in many cases. Okay, another example, these folks are building some city, and they're sitting on this rod. They're very happy right now, but if a bit flip happens on that rod, they're not going to be very happy. So basically, I think of security about preventing unforeseen consequences. It's a very, very general statement about security in general. You can think about this maybe safety also, robustness in general. But we would like to be able to prevent unforeseen consequences by designing our systems to be robust. It's a very difficult problem. It's not an easy problem to enable this. Okay, I like this picture also. We have self-driving cars today that are making decisions for us. Before, in 1990s, Mr. Bean didn't have self-driving cars, so he's driving his own car in a self-driving mode, let's say, and he is the AI engine that is taking the decisions over here. But if a bit flip happens over here, he may not be very happy either, right? This is fun, of course, but you can imagine the real implications, right? As we discussed last time, we talked about RowHammer to motivate intelligent memory controllers. We're going to do more of that. But you know RowHammer, so I'll go through some of these relatively quickly. Essentially, RowHammer is the fact that you can predictably induce bit flips in DRAM chips. And all recent DRAM chips are fundamentally vulnerable. And the paper that I showed you showed that initially. And it's really, what's really fascinating is it's also the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. In fact, this paper was taken by a lot of security folks and shown that, oh, you could actually do all of these different cool attacks by exploiting these bit flips. I'm going to talk about some of them. And you see that people are writing interesting articles that sound like, forget software, now hackers are exploiting physics. And this is a nice, accurate statement, actually, because it's really about physics. What's going on is really about physics. I will not go into a lot of device level works, but I will mention some of the device level works also. So I showed you this paper before. This is a paper that we wrote before the RowHammer paper, actually. It's an invited paper at IMW conference. Essentially, we argued that there are going to be a lot of problems with memory going into the future. We were not the first ones to argue that, but we provide our perspective. And we said that basically we need to solve the issues that we're going to have with memory going into the future, we need to take a much more system level perspective, meaning design intelligent controllers, essentially. And I'm going to present another paper next week, actually, in the same conference, another invited paper discussing what the status is 12 years afterwards. If you're interested, it's also a short paper to look at. Okay, so what are some of the issues? So main memory technology today is DRAM, dynamic random access memory. It was invented in the 1960s by Bob Denard. The idea is very simple. You have a capacitor that stores the charge, and the charge level 1 or 0 indicate essentially whether a capacitor is charged or discharged, indicates whether you have a 1 or 0. And then you have an access transistor that's enabled to share the charge of the capacitor with a bit line and the sense amplification circuitry, so that you can sense whether you have charge stored here or you don't have charge stored here, with some noise margins, of course, right? For this circuitry to work, this is just a single bit. And this is very dense because you can make the capacitor all of these very, very dense, as I'll show you in the next couple of pictures. Basically, this is a charge-based memory. And for this to work, the capacitor must be large enough for reliable sensing. And the access transistor must be large enough for low leakage and high retention time. And all of these structures need to work very well also. So there's a lot of, let's say, art and science and engineering that goes into making this work today, because we're at node levels of 10 nanometers or so. And this is a report in 2009 from International Technology Roadmap of Semiconductors at the time. And they basically said scaling the circuitry feature size, the minimum feature size, below 35 nanometers is challenging. And they were absolutely right. It's actually quite challenging to scale things. But people have scaled down, but it came at a cost. So why do we want to scale the circuit to smaller node size? Essentially, we want to pack more bits in a given millimeter square so that we can have higher capacity memory. Scaling is also good for energy, although that's debatable today, etc. Okay, this is another view of the chip. Actually, if you put it under microscope, you see cells that look like this. It's like this mesh type of structure, hexagonal. This is another view. If you're interested, you can see more videos, etc. So you can see that the capacitors are actually etched into the substrate in a vertical manner. It's like a skyscraper. Some people actually use these analogies. So people actually do a lot of tricks to design DRAM today, which is actually very interesting. Except the difficulty is as the cell size becomes smaller, it becomes less reliable. Right? Charge is reduced, retention time is reduced. As a result, you're more likely to lose charge quickly. And also you're more likely to have noise effects that are disturbing you. And we're going to talk about some of the noise effects today. Does that make sense? Okay. Okay, so we did some studies. I think I mentioned this I don't remember if I mentioned this one in the last lecture, but essentially we did studies with Facebook, for example, at the large scale. We analyzed the memory errors that they see, DRAM errors that they see in all of their data centers. There's actually a lot of memory. It's amazing. This is 2015. We did this work in 2013 or so. They have much more, much more memory today because of machine learning, right? They've actually increased that memory size. I don't know what that is, but the numbers they didn't allow us to publish in 2015. Today, they will not allow anyone to publish probably those numbers. It's a bit crazy. But basically, the takeaway, we analyze all of the errors that that were documented, that were recorded automatically in their memory systems across all of their data centers. And we show that there's a correlation between the density of the DRAM chip that's employed in the server and the error rate that you get in the server. So as memory chip becomes denser, you get more failures. And some of these failures get reflected in the application, etc. Sometimes you need to go and replace things. Yes.
Are there also metrics available for, say, 8 gigabytes or even 16 gigabytes?
Yes, in newer papers. Yeah, this is 10 years ago. At that time, those chips were not there. Today, we have 8 gigabits. This is actually gigabits, but this is a single DRAM chip. So there are certainly newer papers that actually look at this. And the trend is similar, basically. As you reduce the cell size, as you make the chips more dense, you get more errors. But we'll talk about some of the other things. People are also trying to mitigate some of those errors, adding in DRAM, error correcting codes, etc. Okay, so if you're interested, that's the paper from 2015. Okay, so we also were building a lot of infrastructure to understand some of these technology scaling issues, because basically the chips become denser with technology scaling, and technology scaling clearly is good for capacity, but not good for reliability. And we wanted to understand what are the other issues that may come up. This is the first infrastructure that we built. You can see that it's kind of makeshift. And over time, we improved the infrastructure. You've seen these pictures last time before. This is actually where a lot of the RowHammer experiments were done. That's at CMU. And this is the open source infrastructure, SoftMC. You can read papers, the DRAM vendor. I worked a lot on these different topics. He's in the back. He could actually give this lecture also. He has done that before multiple times. And this is some of the things that he has worked on, for example. And this is a prototype. So you can see a lot of these pictures. So why did we build this infrastructure? The actual reason we built this infrastructure was to really understand data retention. Because we believed at the time, in 2011 or so, that retaining charge in DRAM cells actually going to be much more problematic going into the future, because cells are becoming smaller. The number of electrons you can keep in that cell is going to reduce and reduce and reduce, and this is going to become a big issue. It is actually a big issue, but there are other issues also, it turns out. So we had this cool idea, in my opinion, to exploit heterogeneous retention time. So if you look at, because of process variation, DRAM cells actually have a lot of variation in terms of how long they can retain data. At the time, we were refreshing DRAM cells every 64 milliseconds based on the standard. But we asked the question, do you have to do that? And you don't have to do that. And it's not actually a new idea also, but we proposed a implementable memory controller-based solution to actually implement it with low cost. The idea is basically refresh cells with different retention times at different rates. It turns out this is easier said than done. It's actually a very tough problem, because it turns out these are dependent on location. These are dependent on the value pattern here. These are dependent on time. So you cannot just do this easily unless you add error correcting codes, etc. So we wrote papers on this topic. This is one paper that was in ISCA 2012, where we said, oh, if you actually are able to do this, you can get a lot of benefits. You can reduce the refresh rate significantly. Right? You don't refresh everything every 64 milliseconds. You refresh some things every 1 second, for example. It could be 1 second, but yeah, it's possible basically, as long as you characterize it. So we built this infrastructure to characterize the different DRAM cells. And this is actually the paper we wrote, with the first paper we wrote using our infrastructure to understand the data retention behavior. And we said that basically the previous paper we wrote is very difficult to implement in real life. It's a good idea, but it's very, very difficult to implement in real life unless you do something about it. And we basically said, I'm not going to go into the details, but there are issues like variable retention time, data pattern dependence that are difficult to handle. Actually, I don't have another paper over here, but we also wrote a paper in DSN in 2015 to solve this problem in a reliable and robust manner. And it turns out that's going to be awarded the Test of Time Award at DSN, because it's actually a solution. It's actually a very good solution to that problem. It's called Avatar, variable retention time over refresh. And we used error correcting codes and memory scrubbing to understand which cells, for which cells you can actually reduce the refresh rate significantly, which is fascinating. So, okay, so we actually, at the same time, we were building infrastructure to test flash chips. So this is actually very interesting. We have some work in this area, which we're not going to talk about right now, but we'll have one lecture, I think, on flash memory next week, right? So you'll get to learn about flash memory as well, which is essentially all of the storage, all of the interesting, really interesting storage that we have today. I believe flash memory is really an enabler of devices like this. If we didn't have flash memory, we couldn't really store huge amounts of data in devices like this at low cost. But basically, we were building an FPGA-based infrastructure to test flash memory as well. And we actually looked at error patterns in flash memory. This is a paper from 2012 and another paper from 2013. Intel invited us to write a paper in their technology journal at the time to understand the flash memory errors, etc. And it's a more updated paper invited to the proceedings of the IEEE that actually summarized a lot of research that happened over the course of maybe 8-9 years or so, to our research as well as others' research. So if you're interested in learning more about flash memory, this is still a very go-to reference on the topic, even though technology has evolved a little bit over time. Okay, so why am I telling you this story? Because it turns out if you actually are looking at different types of memory and with different infrastructures, you can ask different questions. So in flash memory, for example, we saw in these works that there are some disturbance errors. There are some retention errors, data retention. Flash memory is also charge-based memory, and you lose charge from the floating gates at the time. But there's also a read disturbance. So whenever you access one cell in flash memory, you disturb some other cells. And we asked this question basically, can you have that sort of problem in DRAM as well? And we were quite sure that you could have that sort of problem, but we weren't sure whether you could actually have that sort of problem in normal operating modes in DRAM. So we used our infrastructure to look at what operational conditions you actually would get this sort of read disturbance flipping bits. Okay, so you've seen this picture before. Basically, the idea of RowHammer is, or read disturbance is, in DRAM, you activate one row, which brings the data into the sense amplifiers, which is not shown here. And then you can read the data basically after you activate the row. So you apply high voltage to that word line. And then you actually close that row or pre-charge the bank, which applies low voltage to the word line. And this is a very valid pair as long as you obey the timing parameters. And if you keep doing that repeatedly, which is a valid operation, activate, pre-charge, high voltage, low voltage, high voltage, low voltage. And if you do it enough times before the cells get refreshed, it turns out physically adjacent cells, some physically adjacent cells that are vulnerable, lose their charge completely. Basically, they little by little lose their charge, and eventually their charge gets depleted, so you cannot read them correctly. Hopefully that makes sense, right? So we call this the hammered row, we call this the victim row. We've actually seen this last week before also, so I'll go through this relatively quickly. And we showed in the first paper that I mentioned earlier that more than 80% of the chips that we tested from 3 major DRAM manufacturers, there are only 3 major DRAM manufacturers in the world that occupy more than 96% of the market today, I think, maybe even more today, actually, with HBM, etc. Because HBM is difficult to produce. I should also say that this is a very Western-centric view of the world, because we don't know enough about the DRAM manufacturers in the, let's say, Eastern world that Western world tries to shun away, which is a very dangerous thing to do in the world. Yeah, but again, basically, these are 3 major manufacturers, and more than 80% of the chips are vulnerable. And this is, we showed that this is a scaling problem. We basically tested a lot of modules, I think 129, and we showed that this problem didn't appear before 2010 when the cells were large. We couldn't basically induce bit flips, at least with the patterns that we tried. We induced bit flips in chips that were manufactured in 2010, and all of the chips that were manufactured between 2012 and 2013 were vulnerable. It's interesting. And we said basically because the chips are becoming denser, cells are becoming smaller, you get more vulnerability. And this is going to become, chips are going to become more and more vulnerable. That's why we predicted basically going into the future. Okay, why is this happening? I've already told a lot of this basically. When you access one cell, you disturb another cell due to electrical interference between the cells and the wires used for accessing cells. For example, there are multiple device level mechanisms that I will not go into. There are a lot of device level papers. In fact, we have a paper at VTS that I will flash at you that appeared last month that talks about some of the device level studies, etc. If you're interested, you can go and look at that, for example. But when you apply high voltage to a row, an adjacent row gets slightly activated as well. This is one mechanism. And vulnerable cells in that slightly activated row lose a little bit of charge. And if RowHammer happens enough times, charge in such cells gets drained. Right? That's one way of thinking about it. But there are multiple other things that happen at the device level. The fascinating thing is there's some device level problem over here, or circuit level problem, whatever you want to call it. It's really actually both circuit and device level problem. And now your algorithm and problem and user gets affected. So it has immediate implications because you can induce these bit flips under normal operating conditions in a real DRAM chip using a user level program. Okay, that should not be happening clearly. Right? You should not be these bit flips should not be happening under normal operating conditions, essentially. if you extend the operating condition and if you operate out of, let's say, specification, yes, you may get them. But we showed that a major contribution of this work is to show that you can get these under normal operating conditions. So we showed that using our FPGA infrastructure, and then we basically said, well, can we do this with a user-level program on a real CPU-based system? And that's what we did essentially, using an x86-based system, using real DRAM modules, using real user-level programs, which we open sourced, which Google later built on. I'm going to talk about Google's work also soon. With only these 6 instructions, you can select addresses X and Y such that they map to the same subarray. And basically, what this program does is it makes sure that X and Y are not cached, and X and Y are not in the row buffer also, essentially. And you basically keep doing this. Let me see if I can do this with it's easier here. Yeah. Okay, so you do hammering. And if the chip is vulnerable, you get bit flips. We also said in the paper that if you actually have X and Y, if you sandwich one row between them, you get a lot more bit flips. This is called double-sided hammer. And we characterized that a little bit in the paper, but we should have characterized it more probably. The double-sided hammer is much more effective, essentially. A lot of our characterization in the paper is about single-sided hammering, which is a little bit less effective. But with more patterns like the double-sided hammer, you get disturbance from both rows that you're activating. And there's one row sandwiched. Okay, so this is actually results from running this program on real systems at the time. And essentially, you get significant number of errors, right? And there are reasons why AMD has lower errors, etc. But essentially, you get errors. That's the point. And there's nothing special about Intel and AMD. As long as you're building a good enough memory controller, you get these errors, and everybody gets these errors. IBM, Apple, etc. Whatever. We didn't go and basically kind of make a big deal of it, saying that, oh, you get Apple's. These days, I think people write security papers saying that, oh, we always get, especially with Apple. We get these errors in Apple. Yeah, we could have done that also. But anyway, okay, go ahead.
So, of course, like this issue persists in DRAM, but then the memory controller, are these built by Intel or are these built by, for example, MSI?
Very good question. Basically, memory controllers are built by the processor manufacturers. It was true 10 years ago. It was true right now. And essentially, it's on the processor chip. So Intel builds it, AMD builds it, NVIDIA builds it. So every processor manufacturer builds a memory controller. We're going to get back to that later on, actually. This is a problem, actually. In the IMW paper, next week, I'm going to present saying that this is a problem. We need to be more careful about how we distribute tasks between the memory controller and memory. Does that make sense? Okay, this is a very good question. That was not necessarily the case like in 1990s when there was a separate memory controller chip. There used to be a CPU chip, memory chip, and then memory controller chip. But because of large-scale integration capabilities, Moore's law, memory controller got sucked into the CPU chip. It didn't get sucked into the memory chip because memory chip is not good at logic, if you remember last time. Yeah. Okay. But Intel used to build those memory controller chips also, but there were also other companies building those memory controller chips at the time. Right. Now, Intel could be purchasing IP from some other company, but in the end, they're the ones who are really building the memory controllers. Okay. Okay, so this is the paper. And clearly, if you do this with a user-level program, we said that you could do a lot of bad things. With this user-level program, with some effort, security engineering, you could actually take over a system. We said, for example, you could get hijack control of a system. You could actually crash a system. So those bit flips are obvious to us to actually to make bad things. And we argue that this should be prevented. I'm going to talk about solutions later. But okay, the first people who actually picked up on our work as right after it was published was memory testing software people, the memtest passmark software, for example. This is actually from their website directly. They cite our paper saying that according to the research, basically there's a problem. We introduced, so why am I only getting errors during test 13 hammer test? They introduced a hammer test, which is somewhat similar to what we wrote, but it's not very comprehensive actually. Even then, they received a whole lot of emails and inquiries from people saying that why am I getting errors over here? So they had to add this FAQ, and they had to say that the errors detected during test 13 are most certainly real errors. Basically, there are real errors. They're saying, and you can read about this, which is interesting. So testing is important, as you can see. Okay, so we also said in the paper that this is not good, and we should be basically, I'm going to read the first sentence over here. Memory isolation is the property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. And we said that somebody can write a security exploit. And later, Google folks, Google Project Zero folks, read our paper. They basically did essentially what we kind of said. They used these bit flips to gain kernel privileges using a user-level program. They actually had 2 security attacks. I'm going to talk about that. But there has been a lot of work to use RowHammer to take over a system, which is what the Google folks did. Read data they do not have access to. I'm going to probably flash one of the papers. It's called Ramblete, for example. Break out of virtual machine sandboxes. The Google folks also did that, actually, which is a less interesting attack, but then taking over a system. But if you can do it, this is also good. Corrupt important data, for example. You could corrupt some important weights or parameters in machine learning, and you get very bad accuracy. Steal secret data like cryptographic keys, machine learning model parameters. So you can actually, in the end, cause a lot of trouble. Right? In fact, there's actually a lot of theoretical papers in the 1990s that are written on cryptography. And they basically say, if someone can target bit flips and induce bit flips on cryptographic data, like keys, etc., then all of these security protocols are broken. These are theoretical. And later, a lot of those theory people went into practice, let's say, with RowHammer. RowHammer enabled them to actually really show that these security protocols are broken. Okay, that's very interesting, I think. Today, we're actually talking about post-quantum cryptography, etc. With RowHammer, I'm not sure how that will turn out. Okay, anyway, so this is a copy and paste from Google's blog post, Mark Seaborn and Thomas Dulien. They basically said they learned about the problem from our paper. They replicated the problem on a selection of laptops and found a subset of them exhibited the problem. And they basically built 2 working privilege escalation exploits. One of them takes over the Google native client, which is essentially taking over the virtual machine sandbox. The other is more interesting. Essentially, it uses RowHammer-induced bit flips to gain kernel privileges on Linux when run as an unprivileged user-level process. And basically, the idea is you had the virtual memory lectures 2 lectures ago. So now hopefully you understand this very well. But essentially, the process, the user-level process, is written to induce bit flips and page table entries. And it flips the right bits in the page table entries such that it can get write access to its own page table. And if a user-level process gets write access to its own page table, then it can do whatever it wants, right? Because you know the layout. So that's the idea over here. I'll go through this attack a little bit. But if you're interested, they have a Black Hat talk as well. And Thomas Dulien, actually, he was not working on these topics. He actually has some talks online. And he always says that RowHammer is an eye-opener for him, essentially showing how bad the robustness problems in hardware were. Okay, let me go through this relatively quickly. I already gave you the key idea, basically. Clearly, page table entries. This is slides from Google, by the way. It's Mark Seaborn's slides. Essentially, page table entries control access. And if a bit flip happens in a physical page number, you can get access to a different physical page. Right? And the idea is to do that over here. And to be able to do that, they developed an attack called page table spraying, such that they could maximize the probability of the attack. So basically, all of these RowHammer attacks are probabilistic. You don't have any guarantees that you will get access, but if you're lucky, hopefully you'll get access. And if you try enough times, you'll get access. So basically, these are the x86 64 page table entries. A version of this you have seen 2 lectures ago. So if you actually try to flip the read-write permission bit from, let's say, read to write, you get very little chance, right, to flip that bit because it's only 1 bit out of 64 bits. But if you try to flip the physical page number, it's 20 bits on a 4 GB system, you get a lot more higher chance. So that's the idea over here. The question is, how do you flip that? Basically, you have the virtual address space and you have the physical memory. And what they do is they map a file with read-write permissions. This is the file's virtual address space, and this is the file's physical mapping. And this is basically how you map the file into physical memory. There's some page table entries. The red ones are page table entries. And basically, you keep doing it repeatedly. If you keep mapping the same file multiple times, right? And then virtual address space here, but then physically, you point to the same place. As you can see, you have a lot of page table entries over here. And then you can fill the physical memory with page table entries this way. So each of them points to pages in the same physical file mapping as discussed. There's only one physical file mapping over here. Now, if a bit in the right place in the PTE flips, the corresponding virtual address points to a wrong physical page with the read-write access. Because you open the file with write permission. And if you kind of flip one of the page table entries that are over here, now you can get access to some other page because you change the pointer, right? And you have write access. That's the beauty of this attack, right? Page table spraying. Chances are this wrong page contains a page table itself. An attacker now can read, write page tables. That's the idea. And they can do anything, basically. Okay, does that sound good? I will not go through their exploit strategy, but basically I explained everything. So the key over here is to find out that you actually have right spot in the PT. You actually cause bit flips in the right spot. So basically, there's some process that happens earlier, like search for locations prone to flipping, like some sort of profiling of the memory, like we did actually in a lot of our works. Okay, which is very interesting. There's a lot of work that actually improved on this later on. And later people start drawing pictures that look like this. That's RowHammer. And one of the famous hackers on the internet said, RowHammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. These are real hackers, kind of. It's nice, actually. It's a nice description. Okay, I will not go through all of the security implications, but there's a lot of interesting work, as I said. This is just a selection of the work. These are folks from TU Graz. They basically showed that using RowHammer through JavaScript, they could gain unrestricted access to systems of website visitors remotely. This is work from Kaveh Rezaev, for example, here, which shows that they could gain access to a mobile phone deterministically by exploiting the regular memory allocation patterns in Android operating system. They could fool the operating system to allocate a page table entry to a location that they profile to be RowHammer vulnerable in a deterministic way, because the memory allocator in the operating system follows a deterministic policy, and they could actually take over your system. They had an app for this also. If you're interested, you can download if you're an Android system. I don't know. You can actually accelerate these attacks with GPUs, because GPUs actually can generate a lot of requests, as you have seen with the GPU lecture. You could do these attacks through remote direct memory access engines on a different server also. So you could do it over the network, essentially. And there's another paper that talks about how to do it over the network. This is the paper that shows that even if you cannot take over another system, you could actually read memory that you don't have privileges for reading. It could be some private memory. And the idea is you break confidentiality, basically, as opposed to, let's say, breaking integrity. And the idea is basically you exploit the data dependence of RowHammer bit flips over here, which we will get to, because RowHammer bit flips turned out to be data dependent. So you can actually infer what data you have in a location that you don't have access to by flipping bits around it. Okay, and then these folks show that, along with other folks, you could induce these bit flips in neural networks in a, let's say, targeted manner. And that could lead to very low accuracy in the inference, neural network inference. There's more work in this area that I don't have time to. These folks show that you could do it on FPGAs, and you could actually recover private keys that should not be recoverable again. But it's cryptography, for example, it's one example. Google has some work on this. Actually, Google and Microsoft both developed attacks as well, which is very interesting. I will talk about this later on. This is another attack by Google, a more recent attack from 2021. We'll talk about that, because this also shows that you could actually do RowHammer across multiple rows. We'll get to that. And there may be other attacks like this, right? If your computer is not working, maybe this is a solution, right? Or maybe this is another attack. Again, interesting pictures. Okay, we have a lot of papers on this. I'm not going to cover all of them, but if you're interested, this is actually a paper that was invited to the topics in hardware embedded security in 2019. And even at that time, we thought this problem will be solved, but we were working on actually showing that it's not solved yet. But still, it covers a lot of work. More recently, we've written papers with Ataberk and Giray that talk about that. And our ISCA paper, even though it was rejected the first time, it was invited to the 50 years of ISCA retrospective. If you're interested, you can read it. Actually, the refresh papers, the radar and experimental refresh papers, were also invited to 50 years of ISCA. So people thought that they were actually important to be published at a major, let's say, selection of works from ISCA. Okay, so there's also works from Google showing that Samsung proposed a bad solution. This is actually a very interesting area. These are public works. This is at the DRAM Sec workshop, which is going to happen again in June. So again, you can read this. Samsung had this, let's say, very hard to read paper, and then Google said that it's not a good idea. And more works also show that DDR5 is also vulnerable. This is actually a difficult problem right now. This is from Kave's group also. They basically show that 1 out of 10 tested devices, DDR5 devices, is vulnerable. I believe there needs to be more work to show that DDR5 is also vulnerable. I believe they're vulnerable at the circuit level, at device level. Without mitigations, they're definitely vulnerable. No question about that if you turn off the mitigations. The question is, can you actually flip bits and let's say take over a system, etc., with all mitigations in place? That's actually a good problem to show, especially in the security community. Okay, and this is Girai's thesis. If you're interested in a lot of these, Girai's thesis is one of the latest theses on the topic. He defended last year, and he will receive the major dissertation award from the DSN community, Dependable Systems and Networks community, for this thesis. And also from the computer architecture community, he'll get an honorable mention. So his thesis is recognized by at least two major communities, but two more also, right? Testing and hardware-oriented security and trust. So he may be one of the few people with 4 communities recognizing its thesis in a very, very major way. It's very difficult to do that, I think. Okay, so that's another interesting part of these studies, I think. It's really across disciplines within computer science, right? It involves security, clearly. It involves safety. It involves testing. It involves computer architecture, even though computer architects initially told us that computer architecture has nothing to do with this. But now they're writing papers about it. It involves dependability, robustness. So it really spans across the stack. Devices also, although we don't do work in devices, that's not our expertise, but there are other people who work in device level, and they actually publish very, very interesting papers at the device level. Okay, so any questions? Now I'm going to go into a little bit more detail. Yes?
In the beginning, you mentioned a very specific set of assembly commands in order to introduce RowHammer. Is this more diverse, or because otherwise you could just block this?
Yes. Yeah, that's a very good comment. Basically, for example, CL flash instruction is privileged right now, so you cannot use CL flash. But there are other ways of actually doing this, and other works have shown that you could come up with very different ways of inducing these patterns. So you need to block a really large fraction of things, and people's creativity always overcomes what you block in general. But that's not the only way of doing it. In fact, I'll probably flash another paper where we did with Microsoft that shows many, many different ways, many different types of instructions to do this. But security folks are actually very good at coming up with new ways. Very good. So you can actually, for example, flush a cache line without requiring a flush instruction by building eviction sets. You can actually evict any data you want from a cache, as long as you can build a good understanding of the cache, which many people can today, actually. Okay, so we did a lot of work to understand RowHammer. In this paper, we had a lot of characterization results, thanks to our infrastructure, that enabled us to discover it as well as understand, of course. We tested 129 modules. That's a lot of modules. These are old modules at the time. I'm going to give you a quick conclusions, and then we're going to look at some new works also. And I'm going to tell you a story also, because there's an interesting story, I think, of how this was handled in industry. And maybe we'll talk about the academic story as well. So basically, one of the questions is, what is the adjacency of the aggressor row and victim rows from the perspective of the memory controller? And we found out that most of them are adjacent from the perspective of the memory controller, the distance between the row addresses. 1 - 1, as you can see. But there are some cases where they're not adjacent. And we basically said that this is because there's some mapping that happens after the memory controller. Inside the DRAM chip, row addresses are remapped to other addresses for various reasons. One of them is actually because you may get a fault, you may get a hard fault in one of the rows and you remap the row somewhere else, right? So basically, from the memory controller's perspective, there are some non-adjacent row addresses that lead to bit flips. But physically, we believe that the adjacency, physical adjacency, is really important in the end. And we have some results supporting that, not in this. The question is basically, the reason this is interesting is, can the memory controller solve this problem? If the memory controller doesn't know exactly which rows are going to be flipped, how does it prevent this problem? It could take a very, let's say, conservative approach and refresh the entire bank, for example, but that's expensive. Okay, it's good to keep this in mind. So it's hard to solve this problem without knowing the addresses that are going to be affected when you hammer. Okay, this is access interval. Basically, the idea here is how this is essentially two accesses to the same row or different rows, essentially, TRC. This is not allowed. Below 55 or below 52.5 nanoseconds was not allowed at the time. And if you actually reduce the access rate to DRAM, meaning you slow down the accesses such that you don't access rows as frequently, you can reduce the bit flips, as you can see, right? And you can make this a parameter and say, oh, I'm not going to access DRAM or at least the same row more often than n nanoseconds. If you want to get rid of bit flips, you need to make that value very large. That n needs to be 500 nanoseconds, according to our testing. These are real results showing the errors you get in the worst chips that we've tested from 3 major manufacturers. And this is clearly a bad idea in the end. If you have less frequent access, you get fewer errors, but this is bad for performance also, right? Although GRI later developed a solution that does this in a very selective way. We're going to talk about that. It's called RowHammer, for example. This is the refresh interval. Another lever you can play with is refresh interval. And this is the easiest lever to play with. That's why everybody played with it after our paper. Basically, the idea is if you can reduce the refresh interval, meaning increase the refresh rate, the likelihood that you're going to be able to perform enough activations to induce a bit flip reduces. And these results from real chips support that. Essentially, as refresh rate increases, you get fewer errors. But if you want to get rid of every single error that we saw in our test patterns, you need to increase the refresh rate to be 7x. That's a lot. Refresh is bad to begin with, as we discussed earlier. We were trying to eliminate refreshes. The reason we built our infrastructure was to eliminate refreshes as much as possible, right? Because refreshes are bad for energy, bad for performance, bad for quality of service, bad for predictability. And if you want to increase, if we need to increase refreshes to actually solve the RowHammer problem, that's a bad idea. And our access patterns were not the worst. So the number, if you want to get rid of every single bit flip, actually, you need to increase even more. But basically, this is one way of solving the RowHammer, increasing the refresh rate. Okay. Okay, so data pattern, as I mentioned, some data patterns lead to many more errors because it turns out there's more coupling that happens across the capacitors and the word lines because of the data stored in the capacitors. This is very interesting, and there's more work in this area. And there are actually security works that take advantage of these data patterns to induce more errors and make the attacks more successful. If you use, let's say, not so read disturbance vulnerable patterns, you may not get errors in your chip. So you need to be careful as a security engineer also, or attacker. In the paper, we showed other stuff. One of the important ones, errors are repeatable, meaning if you get an error, if you are able to induce a RowHammer bit flip in a row or in a cell, you will be able to induce it again and again and again and again and again. And this makes this this makes a security vulnerability because now someone can figure out which bits are vulnerable and they can actually attack those bits. We showed that basically simple error correcting codes don't solve the problem. Essentially, you get many errors per cache line. This is very interesting because industry was arguing that error correcting codes solve the problem. I remember very well, I gave a presentation in ISC in 2015. It was in Frankfurt. I talked about RowHammer, memory-centric computing, etc. And then a major memory manufacturer's vice president gave the next talk. And he had the opportunity to actually respond to my talk. And he basically said, we have a solution to RowHammer. And he said, ECC. And everybody knows that it's not a good solution to RowHammer today. Because there are also, it's not just our papers, but it's also security papers that show that even when you have ECC, you can actually take over a system. This is, yeah. Okay. And we talk about double-sided RowHammer. Essentially, a lot of these are studied, all of these are studied in this paper. But later papers actually studied more. RowHammer is getting much worse. We're going to cover that after we cover some more stories. But this is the work that I mentioned with Microsoft that showed like different access patterns, different instructions. And basically, we tried to answer the question, can we guarantee that a chip is not vulnerable to RowHammer? And this is a very difficult testing problem. I think it's very difficult to guarantee that. It's still a good question to ask. If you can find methods to actually guarantee with your testing methods that a chip is vulnerable or not vulnerable to RowHammer, that's good. But as you're going to see, it's going to get much, much worse. So GRI and Ataberk actually had a lot of studies that show that the vulnerability is much more nuanced than it is, because it varies spatially as well as temporally, right? Yeah. Okay, we may get into that. So Girai was a first author of this work that showed that RowHammer actually behaves interestingly with different types of parameters. I'm going to talk about that. This is another of Girai's works on voltage. This is one of Ataberk's work on HVM chips. HVM chips are also vulnerable, basically. Any DRAM chip is vulnerable because fundamentally the DRAM organization is the same, cell is the same. HBM is more interesting today, clearly, because it's the machine learning infrastructure, right, today. And whenever you write papers like this, people become even more interested, although all of these memories are everywhere. Okay, this is another of Girai's work, which maybe talk about. And this is a more recent work that we actually briefly talked about last time, variable read disturbance, that makes a lot of these solutions much more difficult to, let's say, implement. Okay, let's talk about those solutions. Okay, maybe we should take a 10-minute break. Let's take a 10-minute break. I don't think we're going to finish everything, so I'll take a 10-minute break today, but we'll be back and we'll talk about solutions.
You can take mine off on top. You can take mine off. Can I ask a question about the Google attack on the kernels?
Yeah, sure.
Or like the page table, rather?
Yeah, page table.
So I was wondering, I'm not entirely sure because I've visited the lecture like 2 years ago.
Okay.
But the page table in physical memory, it's not it's all in the same like memory region, right?
Or it can be anywhere actually. Yes, it really depends. Yes. Because that also gets mapped to its virtual memory.
Okay. Yeah. So if you were to map the entire page table to like the same adjacent address space, it would probably also not be too smart from a security perspective.
Exactly. Yes. Exactly. Yes.
But otherwise, you could technically protect like highly sensitive areas by mapping empty pages next.
That's true. Yes, that solution has been proposed, except it's very intensive in terms of capacity requirements. But people have proposed that. Yes.
If the page table is everywhere, of course, it gets very resource intensive.
Exactly. Yes. There have been also other solutions that people have proposed, like encrypting the page tables. Those are more possibly doable, but then there's latency overheads associated with those.
And cryptography, it technically still doesn't solve like the issue of RowHammer potentially damaging the kernel.
Exactly. You can damage, but maybe you cannot take over. Yes.
Yeah, definitely. Okay. Thank you very much.
Sure.
Do you think we need this week?
It's not this week, I said, but like for sure. I'd like to meet for sure. Yeah, it's very tight. I will meet. Definitely. You're on my mind for sure. And maybe you'll know a lot more by then.
Well, I hope so.
Yeah, I know so.
Can I actually also ask an administrative question?
Administrative? Okay.
Yeah. About lab 4.
Okay.
So right now we're still in lab 3, and I think the hand-in is next week. So I've heard like the 2 lectures ago, there was a short talk about that we were going to do lab 4.
Yeah.
I assume the lab 4 then starts in the last week of the semester. Or...
I think so, but Mohammed is probably the better person of Constantina. They're the better people to answer those questions.
So I recall that we were talking about. I recall you were talking about lab 4. Yeah.
So yeah, we're planning to release it end of
Last week of the semester.
yeah.
So we're gonna have to include the holidays.
So yeah, but we may make it probably kind of also bonus. So we are also discussing. So it might be also bonus then. That we build into the but we also stretch the deadline. So you guys can have
We can like submit it later on.
yeah, like 1 month or so. Like the whole you can work on it the whole June maybe, you know, and then submit it to you guys. So we want to make it something enjoyable for you guys. But at the same time, I think that is important because that kind of completes whatever we have. So that's why we want to also like some part which is we make some easy part of it as the mandatory part. But then we have a lot of bonus parts.
Like all bonus. And then if we have questions,
Yes, we can also schedule some online meetings also. Like we can
like
say
kind of open hours. You know, some courses have like open hours where you can just come and ask questions. Maybe you could ask exam relevant questions or lab relevant
for
questions.
exam actually we're gonna also have like some discussion or exam related sessions that I will email later and we'll schedule it. For this also because we have a lab session, right? But we can actually use the same slot but not physically. We can have it online.
Yeah.
So, you know, you guys can just send over Zoom and ask questions.
My question is how big the last lab will be because I have the military soon after my bachelor's thesis. So I have very little time to do that for the
Yeah. So the thing is that lab before there are some mandatory parts which we will likely make sure that those parts are not too big. And you guys have more than 2 weeks to be in the lab.
I'm hoping I have the time.
So we will, because then they're not going to be in any other lab after that. So we can also extend the deadline to mid-July, for example. We don't need to have it like
Which is like full time military. So
because the exam is mid-August, right? So we can,
yeah.
To me, actually, we can also do it
When the exam is
because we have to finalize the grades after you finish the exam by end of August or so. So that's the real.
Okay, that's the real part.
We can stretch the deadline for a specific for that work, so that you guys can come together. But there are also but there are some bonus parts, and I think for lab 3 also we are extending the deadline.
Oh, that would
So
absolutely great.
for lab 3
planning to do that all in the next week.
So actually you have time until the end of the
Okay. This is Friday and last Friday.
it was supposed to be next Friday, right? So it's gonna be the next.
Yes, it's last Friday.
Okay.
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 So basically, essentially, therefore, we will release it in June. So, but you guys will have enough time.
I'm just concerned that I'm not doing everything. You know, I don't know if the time to do live packs up until 4 a.m. tonight. That's very good. But after okay, great. Thank you. Those are concerns.
We're so
but I see that you didn't have your background changed enough during the course.
your background changed.
Like when someone left his PC and plugged in, the next time you logged in, you had the cool background picture.
Well, we have Okay, we don't have computer.
Ja, und das muss jetzt ganz verdammt weg von nach China kommen. Let's go hin und her fahren. Und ich sagte auch nur irgendwo anders aufbauen und du kannst es
Oh, yeah, and they didn't need they actually key table clients back to the 20 meter.
Yes,
Yes.
I bin noch so unversöhnlich.
Noch die Stauung respektive die Militärsport gemacht habe ich noch fest, dass ich überhaupt durchkomme. So. Ja, hast du noch ein paar andere Sachen aufgebaut? Es will nicht zu dem. Für mich auch. Ja, ganz ehrlich, mit finde ich sehr schwer.
Das weiß ich jetzt schon. Die einzige Woche, wo ich noch frei. Und mit der das Projekt 4
Du bist gut, man kann ja nachdem dann noch ein bisschen zusammenarbeiten. Ich weiß nicht, ob im Lab für oder Minimum Sachen. Ja, wenn die Minimum
I just got them now.
ja, aber echt flimsy.
Is everything good? Online? Yes? Okay. Okay, let's get started. So let's see. I have about 300 slides. I'm not sure if I covered. Sorry, there's a lot of interesting stuff in this, but you get the gist of it. You don't need to understand the details of every single paper, as you can see. But every single paper builds up very, very interesting things, I think. So let's talk about RowHammer solutions. This is where we argued that you need to actually provide two types of solutions. One is immediate, because you find this vulnerability. All of the DRAM chips are vulnerable, and all memory in the world is main memory in the world is DRAM, right? Maybe not, and over time they'll become more vulnerable. Clearly, there are limited possibilities because we believe that the memory controllers were not designed to handle these well. Increasing the refresh rate is one possibility, for example. We talked about that in our paper, but we'd say that it's a bad idea. So in the future, we should probably look at better solutions to protect future DRAM chips. We should come up with better solutions like programmable memory controllers, for example. So in our ISCA paper, we talked about 7 solutions in total. And our best solution at the time was probabilistic adjacent row activation. I'm going to talk about that. And it was employed in the field after that. But I don't think it's a good solution at this point, at least the way we know how the vulnerability has evolved. One of the solutions was actually adding activation counters per row. We dismissed it, saying that this is too expensive. That's what's happening in industry today. So it's kind of the, let's say, I don't want to call it the dumbest solution that you could come up with, but it's one of the first solutions that you would come up with if you're given a problem like this. Okay, let me add an activation counter per row. There are a lot of issues, actually. Even with that solution, there are a lot of issues, as we will discuss. But I don't think it's the best solution, but at least that's a solution that industry is following, as we discussed last time. But we're going to discuss a little bit more. Now, let me talk about some solution approaches. So you could build better DRAM chips or error correcting codes. I don't think these are good ideas. Error correcting codes are very good at preventing bit flips that are random, but they're extremely expensive when you want to prevent bit flips that are not random. So in this case, you know exactly the error mechanism. It's very expensive to protect everything with error correcting codes, especially if you get a lot of bit flips in a code word. Increasing the refresh rate, we discussed, is again not good for various reasons. Physical isolation, somebody discussed this earlier during the break. Basically, isolate aggressor rows and victim rows, secure the critical data from other data. It becomes expensive, basically, and people have shown that this is not easy to do. So it's vulnerable, actually. So 2 solutions that are actually very, let me see if I have another slide. I don't have another slide, but there's actually another solution, which is remapping. Whenever you have some vulnerability, you remap the row somewhere else. This is also very expensive. It's not in these slides for some reason, but we'll add them later on. That's also very expensive, but people have explored that. I think the 2 very, let's say, promising solutions are reactive refresh, meaning figure out whether an aggressor row is being activated or a victim row is being, let's say, hammered for some reason next to it, and refresh the victim rows somehow. That's one approach. We're going to talk about that. Just the victim rows, not the entire memory, right? Increasing the refresh rate, refresh the memory. There's also proactive throttling, which is basically figure out which rows are hammered and reduce the access rate to those. Basically, slow them down. Don't hammer them, essentially. I think these solutions are actually solutions, and maybe there's a combination of multiple solutions, including ECC, a small level of ECC that could be useful. Now, the difficulty is people are still developing solutions. The difficulty is this complex cost, power, performance, complexity trade-off space in the end. All of these solutions, and there are a lot of solutions that are proposed, and I believe there needs to be more creative solutions going into the future also. There's no single perfect solution in the end. And also the security can be part of this also. So maybe you allow some bit flips, right? As long as they're not exploitable. I don't like that idea. It's not a good idea, but some solutions actually are not secure enough, essentially. Whenever you come up with a solution, it's important to prove the security of the solution. Okay, what did industry do? Basically, industry did what they could do, meaning they increased the memory refresh rates. This is Apple, their security patch. I like Apple because they actually talk about, cite our paper, as you can see. And they basically said, this is a bad issue. A malicious application can induce memory corruption to escalate privileges. This issue was mitigated by increasing memory refresh rates. They didn't say by how much, likely 2x or so. 2x is not good enough to get rid of all of the bit flips. And many other companies released similar patches. And this is the easiest thing that you can do in your memory controller, right? Memory controllers have enough programmability to increase the memory refresh rates across the board in the entire memory. But this is also a bad idea for various reasons, as we discussed, right? For performance and energy. So our solution required changes to the memory controller. The idea is very simple. Basically, memory controller, after closing a row, activates or refreshes selectively the neighbors of a row with very low probability. That's the idea. And if you do this probabilistically with a large enough but low probability, you can be quite secure. It's a probabilistic mechanism, so its reliability guarantee is probabilistic. In memory, actually, you would like to get a guarantee that's around 10 to the minus 15 or so, at least in flash memory, as you may see later on. So we get close to it with P equals 0.05. If you're actually more paranoid, you can increase the probability, right? You could configure this solution. Okay, so that's the idea. And it turns out this is low power, low performance overhead. The slowdown is very low across the workloads we tested for the RowHammer thresholds that we have seen at the time. So the RowHammer thresholds that we have seen at the time, the number of activations you needed to induce a bit flip was on the order of 100,000 or so. Today, we're at a very different regime. So this solution doesn't scale very well, as we will see. But there's a benefit to this solution. Other benefit is, it's basically, there's no cost. You just need to, stateless. You don't need to keep track of anything. Right? You just need to flip a coin. And you can do that actually with random number generation that you do in DRAM, as we have discussed. And it could be zero cost, almost zero cost, low complexity. So it's very cheap compared to the per row activation counter solution that's being implemented today. So I like this idea a lot still. And we showed that basically you could do this in a DRAM chip. You could do this in a memory controller. And if you do it in a DRAM chip, you need to have enough slack in timing and refresh parameters. And with our infrastructure, we showed with other works that there's a lot of slack in the timing parameters. For example, the refresh latency, some of it is just wasted. It's just specified, but actually it doesn't need to be that long. So you could actually sneak in RowHammer preventive refreshes in that refresh latency that's specified by the DRAM standard. If you want to implement in the memory controller, there's some danger here in the sense that the memory controller now needs to know which rows are physically adjacent. So it goes back to that picture that I showed you. Memory controller may not know which rows are physically adjacent. So we said that there needs to be, this is one of the reasons why you basically say you need to have system memory co-design. The memory controller needs to be provided more information about the DRAM chips, essentially, and configured accordingly. And this was implemented by Intel in their memory controllers. So you could actually choose, this is a snapshot of BIOS from one of the Intel machines. You could actually choose your RowHammer solution. Either you pick hardware RowHammer protection or 2x refresh. I don't know why it's so limited. But if you go to hardware RowHammer protection, there's an activation probability that you choose. And you can choose your activation probability. Every 2 activations probably is very expensive. You do refresh every 2 activations, not so good, right? Every 512, which is similar to what we suggested actually, is maybe okay. Okay, so that's the paper. There are more solutions that I'm not going to talk about over here. But basically, our takeaway was, just like we argued even earlier than the RowHammer paper, you need intelligent controllers for solving these issues. And we were doing similar work with our flash infrastructure. If you look at flash memory, you have actually intelligent controllers. You will see flash memory next week a little bit, and you will see how difficult it is to really make it work. There are a lot of issues, and you have to have an intelligent memory controller to actually set the voltages right so that you can read the data correctly in flash memory. And again, if you want to foreshadow things, you can read some papers and take a look at it. Okay, I'm going to give you a little bit more story after this, but basically, the reason I think it's really important there are 2 major directions, in my opinion, to solve this sort of issues. And we're going to generalize this to bit flips later on. Essentially, we don't know enough. To be able to prevent these issues, we need to know a little bit, right? So if you want to prevent, for example, if you want to configure the probability, if you want to configure the refresh rate, if you want to even add ECC, how much ECC are you going to add? You need to know under what conditions these bit flips are triggered, right? And we tested a lot, but there are other things that we don't know enough yet, like aging, for example. If you age DRAM chips 5 years under different conditions, what happens to RowHammer thresholds, right? I'm actually quite interested in this. If it's in space, what happens, right? People are trying to go to space. Do you go there with DRAM? Good luck. maybe you go there with no memory. Environmental conditions. We looked at some of these. Basically, there are a lot of things that happen that affect these bit flips, like memory access patterns, memory control and system design decisions, etc. And then I think there's a solving part. This is all a lot of characterization, basically. That's why infrastructure building for characterization understanding is really important. Modeling also. But modeling is also difficult at the device level. Some of these things are very difficult to model. Solving is important. We need actually more flexible and efficient solutions. Like how do we make it configurable, programmable, patchable, so that if we discover that we didn't do the right thing because somehow some environmental conditions happen, condition under which the system is operating leads to worse RowHammer, you just need to configure things to be better, right? Or maybe you discover some other issue, as we will discuss later on, and then you need to patch things, patch the solutions, etc. I think co-architecting system and memory is important still to avoid performance and denial of service problems, because some of the solutions can cause denial of service, right? For example, if one process is attacking memory and you prevent RowHammer, assuming even with para solution, probabilistic adjacent row activation, but then you deny service to some other process, right? Because you're slowing down the memory access rate because you keep refreshing memory, right? So essentially, even if you're perfectly secure, you may start causing denial of service or performance degradation. And this is a problem with PRAC solution, probabilistic adjacent row activation solution, per row activation counter solution that's being employed in industry today. Okay, so what happened essentially? It's an interesting story. I'll go through some of this relatively quickly, but Intel implemented para, which was a step in the right direction, in my opinion. They wanted to make the memory controller more intelligent, etc. But at some point, DRAM manufacturers said, we solved the problem. DDR4, we don't have this problem anymore. And magically, everyone believed them. I don't know why, but everyone believed it. Even Intel basically stopped their solution. They basically disabled their memory controller solution. Of course, as a researcher, you don't believe that sort of claim, especially with what we know. It's very hard to believe claim. Right? How did you solve it? They basically said they added in DRAM TRR, which we will talk about, which is partly based on the principles of para, etc. I mean, they cannot get rid of the vulnerability unless they move to another device type, etc., or some sort of substrate. That's difficult. So they had to have some sort of architectural solution internally. And we will talk about that. But we also, at the same time, basically we questioned it and we showed that that's not true. That claim is false completely. We also did a lot of circuit level or testing work to show that this is actually a very difficult problem to solve. Much more difficult than we actually demonstrated in our 2014 paper. So we wrote 2 papers. One of them is this one, Revisiting RowHammer. This is part of Jeremy's PhD thesis. It was published in ISCA 2020. And basically here, this is the takeaway. We tested a lot of chips. This is more chips than we tested before. Different types of chips, including LPDDR, DDR4, DDR3. And basically we showed that newer DRAM chips are much more vulnerable to RowHammer. You get more bit flips that happen earlier meaning with fewer hammers. There are new chips like LPDDR whose weakest cells fail after only 4,800 hammers. Don't talk about 100,000, we're talking about 4,800. Double-sided, so double it. So 9,600, still pretty small compared to 100,000. And you get newer technology leads to bit flips in more rows and farther away from the victim row. We basically said that there's this blast radius effect where you can actually get bit flips in farther away rows. And later Google paper, Half Double, actually showed that in more detail. And basically, this is the characterization. We also did some simulation studies to check if this trend continues and the RowHammer threshold keeps reducing, none of the mitigation mechanisms that are proposed is going to be effective. Meaning they're all going to be either not work or performance will be terrible. So these are, I will go through these relatively quickly because I've given you the key results and there's a lot to cover. But these are the chips that we tested. We built even more infrastructure for this actually. And you can see a lot of chips are tested from a lot of generations. I'll give you one result. This result shows that as you go from older DDR4 generations to newer DDR4 generations, regardless of the manufacturer that you have, the hammer count at which you experience bit flips reduces. The first bit flip reduces. You can see that this curve is earlier, and this is the lower hammer count, and also you get more bit flips at a given hammer count. Basically, newer generations are much more vulnerable, as you can see. Okay, I already said this earlier. And this is a simulation study where we studied a lot of the mechanisms that are proposed in literature, including our own mechanism. Basically, we showed that, and this is actually data that's obtained. This is hammer count on the x-axis, and going from left to right, hammer count is reducing, meaning chips are becoming more vulnerable to RowHammer. And you can see that these are the tested data: DDR3, DDR3 new, DDR4 old, DDR4 new, LPDDR4 old, LPDDR4 new. So we're marching towards this side. And you can see the performance impact of the solutions. Increasing the refresh rate leads to a drop in performance by almost 80%, even with DDR3, as you can see, if you want to prevent all the bit flips. Para, which we thought was a good solution, it becomes much worse at very low hammer counts. Meaning if you get a bit flip, let's say after 100 hammers, 100 activations, you lose 80% of your system performance with para. That sounds terrible, right? And we're marching towards that. We'll see numbers closer to 100 soon, even lower actually. This is fast. It's a fascinating graph, I think. Later works populate this part, as you will see. Yes.
Wait, so para is deterministic?
No, that's the probabilistic solution. That's exactly, yes.
To flip once it's being hammered once, right? So if less hammers, it's just more vulnerable. But why does that reduce system performance?
No, you change. Basically, the idea is to prevent all the bit flips. You configure para to make sure you don't get any bit flips.
Oh, so you increase
exactly. You increase the probability. Exactly. Yes.
Okay.
Exactly. That's why performance decreases. Even the ideal mechanism actually decreases. Yeah. Okay, so there's basically a significant opportunity to come up with new RowHammer solutions. And after this, a lot of people started even more RowHammer solutions. There were works, but more works happened. So basically, key takeaway: RowHammer is really a technology scaling problem, and finding a solution to it is difficult, and it will become more so. And this is still true. Finding a good solution, I should say. Okay, so this is an example over here. These are the reported HC first or RowHammer threshold high, a number of hammers for the first bit flip values. Ideally, you're infinite. And if it's one, that's terrible, right? With the one activation, you'll get a bit flip. So we're marching from left to right over here. This is HBM also with older technology. That's part of Atavark's work. Okay, so as I said, we also questioned whether the claim of DRAM manufacturers is true. And together with Kave's group, we published this work at IEEE Security and Privacy, concurrently with ISCA paper that I mentioned earlier. And the idea here was to ask this question, basically. Are the solutions good, right? Or can we bypass them? And basically, we were able to bypass them. TRR is essentially memory manufacturers added this target row refresh, which is a very vague mechanism that's added to the standard. It's not a mechanism, actually. It's really a way of solving a problem. They basically said you could send target refresh commands from the memory controller, and this would refresh something. Is that a correct characterization? Maybe it's a little bit better than that, but basically, this is a way of actually solving the problem. But they didn't disclose what they did internally. So clearly, there needs to be a mechanism for detecting, for example, when to refresh something. Right? It's clearly a refresh-based solution, but what do you refresh and when do you refresh was not disclosed by the manufacturers. They basically were doing security by obscurity and claiming that, okay, based on this, we solved the problem. So we basically hypothesized that internally there had to be a mechanism that keeps track of some of the rows, and that needs to keep track of some sort of a way of which rows are frequently activated, either probabilistically or deterministically, and then decide what rows to refresh. And that's what we did, basically. And we basically said, maybe there's a table internally. This happened, of course, with some testing of the DRAM chips with our FPGA-based infrastructure. If we didn't have an FPGA-based infrastructure, we wouldn't be able to come up with this attack or show this easily at all, actually, maybe at all. So basically, we said that if you hammer many rows, not just 2 rows or 1 row, if you hammer many rows, maybe you will overflow the internal tables that are there to detect aggressor rows. For example, if the DRAM manufacturer puts a table over there to keep track of 4 frequently activated rows with some way of detecting frequent activations. That's also a difficult problem by frequent item counting. But let's assume that they did it. If I actually hammer 5 rows very frequently, they will not be able to detect one of them. Right? So I will overflow that table. And that's essentially what we did. To be able to do that, we need to reverse engineer the DRAM chips and the memory controllers, again, with our FPGA-based infrastructure. And we actually provide an automatic tool that can effectively create many-sided RowHammer attacks. So these are some many-sided attacks. So this is double-sided, only these red rows, and then there could be a three-sided attack, as you can see. The red ones are the hammered rows. You can see that this is four-sided. Red ones are the hammered rows. Again, if the manufacturer is only keeping track of 2 rows, then we could bypass it. Of course, there are some other considerations, and these are from real chips again. We were able to induce bit flips, for example, after we hammer 5 rows in this particular module, after we hammer 7 rows in this particular module, 9 rows in this particular module. And bit flips are not like deterministically increasing or decreasing because there's some internal mitigation that we didn't completely reverse engineer. Later work, we're going to completely reverse engineer, almost complete. And this is a table from this paper that's showing that we weren't able to induce bit flips in all of the chips we tested, but we were able to induce bit flips in enough chips that we thought this was important to publish and write. Because the claim was, there is no bit flips, right? Now there are bit flips, except you need to work a little bit harder. And in some cases, for example, the best pattern that we found was 19-sided, 19 rows being hammered, right? It's interesting. Okay, this is very interesting. And we were able to show that you could take over, you could launch different type of attacks on mobile phones, different mobile phones. Again, if you try harder, you can get all of them to be checkmarked, meaning you could actually induce bit flips in all of them. And we were able to replicate different attacks on different modules, like page table attack that we discussed, RSA attack that we didn't discuss, but it's essentially getting the encryption keys, etc. And you could do it relatively quickly in many cases, right? So these are real attacks on systems that are claimed to have completely RowHammer free chips. This is actually RowHammer free is the what manufacturers said. Okay, so this is the conclusion of key results. And we basically said that this is not exhaustive. These results are scratching the surface. There's a lot more room for uncovering more vulnerable chips, essentially. Sounds good? So basically, the takeaway was RowHammer is still an open problem, despite the claims. And security by obscurity is likely not a good solution. I still believe this. But we're still doing security by obscurity in current solutions because we don't know exactly how the internal solutions today work. A little bit more we know, but still not enough. But the bar is a bit higher because it's harder to induce bit flips now because there's a lot more going on inside the DRAM chips. Okay, so these two works actually cause a lot of churn in JEDEC, which is the standards body in DRAM. A lot of people said, okay, what's going on? You said these chips were not vulnerable. Now they're vulnerable. Well, there are 2 studies that are showing fundamental issues. So people got together and they wrote not so great white papers. They reference our papers, but I think some of the solutions are actually very, very weak. If you want to look at, it's interesting, but I don't think these are, let's say, solutions themselves. These are more like, oh, how do we brainstorm about solving the problem type of papers. Do you agree, right? Yeah, but they do actually reference these works. Say it again.
Near the guidelines.
Guidelines, yeah. I'm not sure if they're good enough guidelines either. Okay, but more recently, as I said, there was a more, let's say, concerted effort. But this took about 3-4 years, as you can see, to have a more, let's say, better framework for a solution around per row activation counters, which we talked about last time. I'll go through that a little bit more, but you got the basic idea. And this was standardized in April 2024. And as far as we know, all DRAM chips are going to implement some version of this, but we don't know exactly how it will work. Okay, so we did more work on uncovering this target row refresh almost completely. I will not talk about this in detail. It's actually fascinating. You can uncover a whole lot of almost everything. If you spend enough time, you can figure out exactly how the solution works. This is Hassan's work, part of his thesis. And the idea is, I'll give you the basic idea, but I will not talk about the detailed results. The idea is very, very interesting, I think. What you can do is you can profile the retention time of rows. And you know that this row is supposed to retain data for this long, right? And then you can launch a RowHammer attack. And you figure out whether that row would retain that data. If the row did retain its data, that means that somebody refreshed that data. So you reduce the refresh rate, you get rid of the refresh rate, you get rid of refresh or do something that's enough. But launch a RowHammer attack. And the RowHammer attack is supposed to take longer than the time the row is supposed to retain its data. So the row is actually not supposed to retain the data that you wrote over there. But internally, there's some mechanism that refreshes the row. So if you can actually figure out that there's an internal mechanism that refreshes the row and the row retained its data, you can figure out that there's something going on internally. Right? You know the retention time, the row is supposed to lose its data, but it didn't lose its data, so somebody must have refreshed it. That's the idea. Then the question is who refreshed it and how often did it refresh it? So you can actually figure that out with the methodology. Okay, so we figured out a lot of things based on the DRAM, based on this methodology. And you can see, for example, some of the aggressor detection mechanisms are counter-based, some of them are sampling-based. So there's some probabilistic mechanisms that happen. Some of them are mixed. You can see some of them are doing per bank detection, some of them are not doing per bank detection, etc. Some of them are refreshing 4 neighbors as opposed to 2 neighbors. So there's some, which makes sense also because RowHammer affects not just the immediate physical neighbor, but also maybe a little bit farther physical neighbor as well. In the end, what this work showed is that you can bypass essentially all the modules that we tested. And almost all of the rows in a DRAM bank experience at least one RowHammer bit flip using our mechanism. And ECC is completely ineffective. So this is another work that shows that ECC is completely ineffective. You get up to 7 RowHammer bit flips in an 8-byte data word. Clearly, I mean, ECC is effective if it's very strong, right? But very strong ECC is expensive. Okay, so there's more results here. How much time do we have? Any questions? Okay, 25 minutes. There's still time. You can still ask questions. So this is fascinating. But later we looked into more RowHammer characteristics. This is a paper that Girai was the first author on. We looked at temperature, how that affects RowHammer, aggressor of active time, and physical location of a cell. Again, I will not go into details over here, but it's fascinating to study temperature. So there's no easy relationship between temperature and RowHammer vulnerability base. Different cells behave differently. And there's a bounded range of temperature where a cell happens to be more vulnerable to RowHammer. I don't think we quite understand this yet. Do we, Gary? Sort of, yeah. He doesn't understand fully. Okay, there's more, maybe more needs to be done over here. It's very different from retention time, for example. Data retention time has an exponential relationship with temperature, meaning retention time reduces exponentially as temperature increases. Whereas RowHammer, you don't have any such relationship. Okay, basically, this is the second observation led to row press, which we have discussed briefly, which we will discuss a little bit more. If you actually keep the aggressor row active a little bit longer than the minimum interval specified inside the DRAM data sheets, you can induce more bit flips. That's the idea over here. And if you actually, row press later extended the study to be much wider, longer time intervals. And certain physical regions are more vulnerable. So why is this interesting? Basically, it's interesting for developing better defenses, because if at some temperature level or at some physical region or at some active time, you're much more vulnerable, you need to change your mechanism, right, to take that into account. Otherwise, your defenses may not work. It's also good for an attacker perspective, because if an attacker knows more information like this, they could do a better attack. So it's always, if you know more information, you're a better attacker as well as a better defender. Okay, this is one example over here. If you keep the row active a little bit longer, you reduce the hammer count to induce a bit flip by 36%. And if your configuration of the defense assumes some hammer count, that's not taking into account this 36%, the attacker can do bit flips basically. Okay, there's more over here. For example, if there's this paper shows that more than 90% or around 90% of the cells are much less vulnerable to RowHammer, and a small fraction of cells are much more vulnerable. So why not design protection mechanisms that take this into account, right? You're more aggressive in the protection over here, and you're less aggressive in the protection over here. You can reduce the area overhead or the performance overhead of the defenses this way. Okay, and Girai giving a talk on this topic, as you can see. Okay, there's more RowHammer analysis, which I will not talk about. I'm going to skip this one. These are very interesting studies to do because we need to fundamentally understand the problem. Like, how does this change with voltage, for example? So Girai updated the infrastructure to be able to do that. There's a summary. Interesting. I will not talk about that. We asked the question, does this happen in HBM chips? I mean, we knew that it happened in HBM chips, but to what extent, etc. So you can read more about that in these papers. Girai wrote papers on the spatial variation of RowHammer. There's a lot of interesting data over here, which I will not talk about. But you can talk to him if you want. So let me talk a little bit more about, let me switch to the attacks and solution side, and then we're going to probably get back to characterization. So there was other people also doing things. I mean, infrastructure-wise, not many people did studies using real DRAM chips using FPGAs. More recently, there are actually papers coming up because we open sourced our infrastructure and more people are actually doing work in this area. But people are also working at the system level and developing more attacks. Google actually built a simple infrastructure, and they basically showed that you could induce bit flips with an aggressor row that's far away from the victim row. So this is classic RowHammer. You have an aggressor row, you keep activating that row, and you have victim over here. In this half double attack, they called it, you activate aggressor row A many times, and then you activate aggressor row B a few times. And this causes bit flips in victim C. So the aggressor row B activations can be, I don't know, 100, let's say. Now, there are two interesting issues over here. One is, if you didn't know this, maybe you configure your RowHammer defenses such that you only take into account aggressor A activation. So you set your RowHammer defense to kick in after maybe 10,000 activations, right? Whereas the real number should be 100 over here, right? Because you activated this 10,000, but then what about this one, right? That could activate only 100. Okay, there's another issue. This one, if you keep activating this and your defense kicks in at some point, now your defense becomes an attack. Because what your defense would do is it would refresh these aggressors, and that refresh is an activation, right? Now your defense becomes an attack on the victim, which is very dangerous, as you can see, right? So that's why this is very interesting, I think. And you can read the paper for more detail. They wrote a paper. They first published a blog post, but then wrote a paper at Using Security after some time. Okay, so Microsoft was also doing work in this area quite a bit. And these folks actually, I will not go into this in detail, but they basically showed that you could induce these bit flips using coherence mechanisms in existing CPUs. If you want to know, you can read the paper for more detail. And basically, even non-malicious code can actually induce these bit flips, like in commodity workloads, because of coherence mechanisms. It's actually interesting because there was work in 2012 or so at Intel that showed that there are some workloads, there are some benign workloads that induced bit flips in real systems, real DRAM chips, and they were actually also related to coherence. Okay, so they kind of rediscovered something that was never documented, let's say, properly, in my opinion. So we spent a lot of time at Intel in 2012, so a lot of interesting things. Okay, so GRI developed this BlockHammer solution. I'll go through this relatively quickly because this is an out-of-the-box solution, relatively. A lot of solutions were basically, let's detect the aggressor rows and refresh adjacent ones. This solution doesn't say that. Basically, the solution tries to do something different, and it also tries to remain compatible with commodity DRAM chips. So if you want to actually detect, if you want to refresh adjacent rows, you cannot implement that solution in the memory controller perfect, because memory controller doesn't know which rows are adjacent to each other. But memory controller knows which rows are being activated. So in this work, the idea is to use area efficient balloon filters to detect which rows are being activated a lot, and you selectively throttle accesses to rows that are activated too much, dangerously, let's say. Basically stop the accesses to that row until you think it's safe. So there needs to be some security proof, and GI provides that proof here. And if you actually do this, you can also inform the system software about something that keeps activating rows a lot, right? And this is the advantage of this work is it's compatible with commodity DRAM chips. You don't need to know the remapping or mapping of rows inside the DRAM. There's no need for proprietary info or modifications to DRAM chips. You could implement it perfectly in the memory controller. The key is basically designing this to work well. Yes?
Isn't that a bit dangerous? For example, if you have like memory mapped input-output operations that tends to access a certain memory region a lot.
A lot?
If you have
yeah.
like a very high frequency device that communicates over a memory mapped region.
That's good. That's a good question. But then you probably wouldn't be accessing DRAM, right? Because they're memory mapped to some device, and you would be going to that device. Yes. I don't think there's any reason to access DRAM in a case like that. It's just you use the memory mapping as a way of identifying the device. But that's a very good question. It's good to think about these corner cases, right? Am I accessing memory in some way? I don't think in that case it's a problem. Okay, so this is an example of a more intelligent memory controller, as you can see. It's a little bit more intelligent. It's a little bit more expensive also, and it's less scalable, as GI also showed. But you can also download the source code. A lot of these, almost all of these works have their source code downloadable. Even our original RowHammer work, we uploaded that 6-line assembly program, if you remember. And Google built on that program to actually build their RowHammer attack. Okay, so essentially this is an example of intelligent memory controlling. So these are the solution approaches. I will not go through in detail again. There's more to be developed here, and I'm going to flash a lot of pictures. But let's what's happening in industry. As I said last time, essentially SK Hynix published this paper finally in 2023. This is the first, let's say, paper written by a DRAM manufacturer that's acknowledging the problem, RowHammer, that's citing papers, and also saying that we try to solve this problem, introducing per row hammer tracking, which is essentially similar to PRAC, per row activation counters. And it's essentially a DRAM controller implemented inside the DRAM chip to hopefully avoid bit flips. Although if you read this comprehensive scheme leads to a reduced probability of failure due to RowHammer attacks by 93.1%. Meaning there's still 7% or 6.9%, even with this cryptic thing. There's not much information. You cannot understand this, what's exactly done. But at least the high-level idea is every row has an activation counter, and with some information, this activation counter gets incremented. At some point, if this is greater than some threshold, you refresh some adjacent rows. Exactly what is refreshed and when it's refreshed is not described. But step in the right direction, hopefully. Maybe not the best solution, but at least an intelligent controller is happening over here. The problem, one of the issues is this. This is done with the standard DRAM interface. So if you're not able to refresh the rows while the accesses are coming in, you may still get bit flips. Right? Basically, the memory controller is sending requests as well, and the DRAM chip is internally doing something. And if the number of refreshes that you need to do while the memory controller is sending requests is a lot, then you may not be able to do the right thing and refresh the rows, right? Because at some point, basically, if there's too much that you need to refresh over here, you need to tell the DRAM chip, stop. I need to do something internally, right? And today there's a way to do that with DRAM. It's called an alert signal, which is a very interesting signal. It's not used a lot. Alert means basically I have some error. In the end, the PRAC solution relies on this alert, but we have a better interface solution that I will briefly describe. Okay, this is Samsung's paper that Google showed was broken. You can still read it if you're interested. This is a paper from Microsoft that talks about these per row activation counters, which had a lot of influence. Microsoft actually pushed the solution a lot. And eventually it got, let's say, standardized in JEDEC. The question is, are these good? We wrote papers at DRAMSec last year and also more recently at HPCA. Again, Giray mentored the student who wrote these papers, right, Giray? So Giray can present this talk. But basically, this showed that these solutions work. They can be configured to be secure and safe, but under conditions where when the RowHammer threshold is low, you will get very high performance overheads. Even with not so low performance thresholds, you get some performance overhead because these solutions change the DRAM timing parameters. So we propose some solutions to actually reduce the overheads, etc. Again, if you're interested, you can read. Okay, the question is, are we RowHammer free? Have we gotten rid of bit flips? And I believe that the answer is no. We didn't talk about row press, but I will talk about that very quickly. We talked about that very briefly last time. This is something that we wrote to ISCA in 2023. And the idea is to find mechanisms or phenomena that doesn't require high row activation count. So this is a row press paper. If you're interested, you can take a look at it. But the basic idea is it's different from the RowHammer vulnerability. It's a different row read disturbance phenomenon. And using a user-level program, you can induce bit flips when you cannot induce with RowHammer in some chips. And there are some solutions that are provided. So what's the idea? If you keep the DRAM row open for a long time, this causes bit flips in adjacent rows. They do not require many row activations. In fact, you can reduce the activation count by 1 to 2 orders of magnitude. In fact, this is fascinating. Only one activation is enough in some cases. You activate the row, keep it open for 30 milliseconds, which is not allowed in the existing standard, but it's important for fundamental understanding of the device from my perspective. You keep it open for 30 milliseconds and you get a bit flipped. That means that this fundamental operation of keeping a row active, the row buffer, the sense amplifier is connected to the cells, leads to some disturbance to physically adjacent rows with just one activation. Okay, good to think about. And this was not documented in any device level studies. So RowHammer was actually studied at the device level a little bit. But here, we basically showed this phenomenon, and later device level people tried to explain why this is happening. It's actually very interesting. That's why I see the lab that we built as a lab for discovery. It's more of a science type of lab to figure out what's going on. And then later people can explain the situation, right? Okay, so, I think I've already said this, right? What if you configured your defense, but then you figure out some other phenomenon leads to a low activation count, and you cannot configure it. So this is the difference between RowHammer and RowPress. RowHammer, you keep activating at the maximum possible rate. RowPress, one example, you keep the row open for long. This is allowed, 7.8 microseconds. Memory controllers actually can keep the row open 7.8 microseconds. And it can reduce the activation count by an order of magnitude, let's say. Okay, so we studied this with our infrastructure. We studied many manufacturers. And initially in our papers, we used to not tell the names of the manufacturers, but now we tell the names of the manufacturers. I think it's good for replication of studies. I already said the amplification of the DRAM's vulnerability, but it also has a different underlying error mechanism than RowHammer. So this is the major result, essentially. If you look at these three manufacturers, Samsung, Hynix, and Micron, this is RowHammer. You basically activate a row every 36, you keep a row open for only 36 nanoseconds before reactivating it. And as you increase that interval, you reduce the activation, minimum activation count to induce a bit flip significantly, as you can see, right? By 1 to 2 orders of magnitude. So 7.8 microseconds is allowed. 70.2 microseconds is also allowed if you do refresh scheduling in DRAM. So this is the allowable range. 30 milliseconds is not allowable range, but it's important to study. And you can see that you get bit flips in these chips with a single hammer count. So that's very interesting. Okay, so basically, where are we? According to RowPress, you can get bit flips with 380 activations or 335 activations with HBM. Altabark studies the RowPress phenomenon on HBM. This is a very low number. So there are some workloads that actually activate a row maybe close to 1,000 times in normal operation mode. Basically, you don't. It's not a malicious workload; it's a benign workload. So how do you solve this problem? This becomes worse, actually, as you see over here. If you actually increase the row on time, this is still allowable, 70.2 microseconds. You get a bit flip after 51 hammers, 51 activations. It's sad. The question is, of course, this is benign. It may not be exploitable easily, but if this benign workload actually induces bit flips, and it's actually doing this a lot, then either you get bit flips or you have a secure solution that solves this problem. But the secure solution at that activation count is going to be very expensive, right? In terms of, because it'll keep kicking in very quickly, and then it will generate these refreshes or throttle the rows, and as a result, your performance will tank. Yes.
What's the key reason is actually there to even allow such long row on times? Is there like a certain reason why this is necessary to even allow?
That's a good question, basically. I mean, solution will actually is going to limit that row on time. Today, it's allowed for keeping, if you keep the row open longer, what you can do is you can exploit the row buffer locality. That's the main reason. Because there may be more accesses coming in, and they could easily come within 70 microseconds. Right? Milliseconds is questionable, but microseconds, they could easily come. Okay, so that's the reason. But if you limit that a little bit, then you can solve this problem more easily. And existing memory controllers actually keep it open, as we will see. You had a question also? Yes.
What physical property changes if the capacitor is also basically the transistor over the capacitor is turned on? Mm-hmm. So why does the capacitor basically influence the other row in on state but not in off state?
Oh, okay. Basically, there's no leakage that happens, right?
Okay.
If in the off state, you don't have any leakage, but in the on state, because different rows share the substrate, underlying substrate. I didn't go into device level mechanism. I have some slides at the end. They share the substrate. In the on state, there's electrons leak. Very good questions. Okay. Okay, I think I've said a lot of these, but basically, this gets worse as temperature increases. It affects a different set of cells than RowHammer, which is also interesting. That behaves differently as access pattern and temperature change compared to RowHammer. So we basically declare that this is a different phenomenon than RowHammer, even though it's related. And later, device level works actually proved that with their simulations. So we also showed that you could actually keep a row open in an Intel system using some memory by accessing different cache blocks in the row. So this is again a user level program that keeps accessing different cache blocks in the same row, and the memory controller keeps the row open. For example, we keep accessing 32 cache blocks, 48 cache blocks, 64 cache blocks, and essentially we get bit flips with row press, whereas we don't get bit flips with RowHammer, for example. So you need to keep the row open long enough to get bit flips. And these are real results. Later works from other people have replicated these results. I might mention them. So row press is also a real phenomenon. It's a bit harder to induce than RowHammer clearly on a real system, but it's possible to do it. Okay, so how do you mitigate this? Basically, as you can kind of alluded to, you can limit the maximum row open time, but you don't want to limit it too much. If you limit it too much, then you're not exploiting row buffer locality. So we basically said, find a sweet spot, hopefully not 7 microseconds, keep it lower. You make a trade-off. You exploit less row buffer locality, but you also reduce the, you're not as vulnerable if you actually use a much unlimited, let's say, row open time. And you configure the RowHammer mitigation to account for the row press induced reduction in AC-min. That's the idea, right? You could do that. So basically, you could adapt all of the RowHammer mitigations that are proposed to row press, but it comes at a cost. You start, essentially, you start preventing bit flips or taking preventive actions to prevent bit flips at a much lower activation count. Okay, and these are the results. We showed that basically if you have row press and if you want to mitigate it, your performance overheads increases with different mechanisms. Okay, and this is a paper that was published. It got the Distinguished Artifact Award from Micro. So the artifact is nice. You can build on it if you're interested. And also it was selected as a top pick. So you can take a look at it if you're interested. So there's more to come, I think. Let's see. I think we're getting close to the end. Okay, 5 minutes. 5 minutes and 100 slides. Let's see. We're going to try. Hammer. Okay, so I've already said this. So I'm not going to talk about this. So if you're interested, you can read more papers. So this is RowHammer and combining RowHammer and row press, which is interesting. There's more studies. This is another work Guy did. Guy did a lot of work for his thesis. So he deservedly got those awards. So we always argued for better communication between DRAM and controller also. I think one of the interfaces that's broken today is the interface between memory and the controller, as we've discussed multiple times. So this work, self-managing DRAM, which was published at Micro last year after 6 rejections, because people either thought this was not interesting or this was too revolutionary, which is kind of interesting, right? Different reviewers think differently, right? What did they say, revolutionary or?
They said it was too early to publish this paper.
Okay, yeah, right. Well, they said something else also. It was close to revolutionary, right? Okay, anyway, so the basic idea is very simple. It's actually a very small change to the interface. The idea is to enable autonomous maintenance in DRAM because there are some things the DRAM chip can do without requiring the memory controller, like doing refresh, for example, or doing RowHammer mitigation. If you actually, it has some intelligence inside, it can do much better refresh mitigation, retention time mitigation, RowHammer mitigation, memory scrubbing, error correction, etc. The problem today is memory controller very tightly controls DRAM, and DRAM cannot initiate anything by itself. So it cannot say, oh, I'm going to do RowHammer mitigation. It can, but it's limited as we discussed with PRACKR. So our idea was to say, we make one single change to the DRAM interface and enable a lot of optimizations in the DRAM chip without requiring the memory controller to change or without requiring the memory interface to change. We argue that this would be good for multiple reasons because you could actually implement these mechanisms nicely and easily over here. This also decouples the innovations that happen in the DRAM chip from the interface. Now your interface doesn't need to change, but a memory manufacturer can implement some innovation over here. So nobody needs to wait for 10 years, 20 years, etc., to change the interface because interface change is a huge problem in this area. Or you don't need to change the memory controller either. So that's the idea basically. So the idea is, again, what's the interface change? The interface change is very simple. The DRAM chip can say no to the memory controller in a fine grain. If the memory controller says, activate this row, DRAM chip says, no, I'm busy. That's it. That's the only interface change. I don't know what's revolutionary about this, but Apparently it's revolutionary. I mean, there are implications, of course, right? Where does the memory controller now reside, right? You asked that question earlier. Now, part of the memory controller resides over here, right? And some people don't want to give up the control. Okay, even though the system will become better. So basically, memory controller orchestrates accesses. DRAM chip does what it's good at, performs maintenance. Right? So I think this is a very principled approach to partition that work nicely between memory controller and DRAM chips. And we showed that you could actually implement a lot of DRAM refresh solutions that are proposed in literature, a lot of RowHammer solutions proposed in literature, memory scrubbing solutions proposed in literature, and get good results. And I'll let you read the paper. This was part of Hassan's work, but Atabak presented because this got rejected 6 times in the end. The fact that, say it again?
Did it get accepted?
Yes, it got accepted in Micro 2024. I think we start submitting in 2022, right? And nothing has really changed in the work, like evaluation and writing changed a little bit, but the basic idea doesn't change. And when it was presented at Micro, somebody came up and said, "This is a great idea. This is it's a principal solution to this problem." Yeah. So great ideas get rejected, basically. That's one of the takeaway over here. I believe this is actually a nice idea, and we need to do more of this. This is it. So, okay, another way of thinking about this is, okay, I'll stop here after that. But now what we're doing is, if you think about the memory controller controlling everything in DRAM is a very processor-centric approach. Processor sits here. We're very processor-centric. What we're saying is make the memory controller a little bit more memory-centric. That's the idea. I think it's a move towards more memory-centric directions. In fact, in the paper, we say that if you actually have this sort of interface, you could also implement processing in memory operations more easily, etc., in the DRAM chip. Again, I'll leave you with that. I didn't cover all of my slides, but that's okay. No problem. If you're interested, you can look at the remaining ones. Or maybe we'll start with part of this next week. Okay. I'll see you guys next week.